we tried many different way of class, such as online and in class together. And through homework, we made a group, and in group, you share and collaborate and discuss and working on the task together and submit a homework together. And each is not homework, it's a group task. And a group task, based on group task, a group will have share the same grade for each task. That's another new trial. And we share your all PPT file through PowerPoint sharing method, and using KakaoTalk, we share all the information and get the feedback. And YouTube, you use YouTube to upload your all homework. One of the most important point of your submission of your report is that through oral presentations rather than just writing. See, oral presentation is very important. Say you sitting there and you listen, I'm sure most of you understand a certain concept. But when you want to explain some concept to others, that could be a little different story. When you are able to explain from yourself, then you fully understand. So it's important to keep practicing, speak up. Any topics you want to say, okay? I cannot emphasize enough, but it's so important. So that for that purpose, we use the YouTube. Well, it was okay. I'm pretty much satisfied the way you submit reports, and I'm very happy. But sometimes it's not so convenient. But I hope you students need to understand we are a moment when we are going through all paradigm change for educations, and not only from a professor, but also from your side. So it is the concept called PBL, problem-based learning. Nowadays, all over the world, many universities trying to change the paradigm of the educations. We all need to understand why. I mean, conventionally, the education as a class is just a deliver knowledges, right? Deliver knowledges. But these days, we need to, more importance goes to creations from your ideas through collaborations, okay? So those are two keywords, creativity and collaboration. Those are two key, very important keywords in educations. So, so I tried a different method. Some is new to me as well, but in many cases, I'm pretty much happy with your attendance and your involvement in this class. Okay, I don't know how happy you are in this class. I hope so, but this kind of change will continue to not just my class, but continue to happen in other classes as well. Okay. But the most difficult part is the exam, right? Which we have to go through. So as I mentioned, this final exam, there are several topics you have to go through. First one is the thin wall shaft. What is a thin wall? Thin wall shaft is not just a solid cross section, it's a thin wall. It's like wing and two, a lot of structures is made of these thin wall shafts subject to a torsion. So we need to understand the behavior of a thin wall shaft. Very practical case. So again, feel free to ask any questions, okay? First one is the thin wall shaft. Cross-section shape can be any shape, can be circular, can be any shapes. But there is another thin wall shaft is the open, like this and like that, or I-beam. This is all thin wall shaft. And the way we calculate is quite different. First of all, this one, there are two main topics, shear flow. How we calculate the shear flow? Shear flow is Q. That is the approximately a shear stress times the thickness, right? Shear stress in times the thickness. Thickness is this one. And thickness can vary, by the way. Doesn't have to be constant. And this one is the torque we apply. Apply and then 2 minus A. What is A here? What is A?
Area.
Yes, area is the A is the area of these closed sections. Okay, so this is the shear flow. This is a stress. Now, second one is the angle of rotations. Angle of rotations. Okay, angle of rotations. The theta. Now, this theta is not a simple formula. It has involved a certain integration. I would like to show which the slide we went through. No, not this one. The thin wall, this one. See, this thin wall is a closed one, by the way. There is a gamma, this is the gamma, and this is the shear stress, shear flow, and G times the thickness T. Basically, this comes from gamma, tau G gamma. So gamma is a shear strain, two angle shear strain. So we integrate both parts and come up with very important formulas. And d theta dEz is the rate of the twisting angle. So if any cross section, if you have a certain length L, and then at the top you have a theta, this will be simply theta over L. So theta for given this you can see that okay, from these equations, as you can see that QL and 2A and divide ds and gt. Well, it looks a little bit complicated, but we need to understand what it means by S. What is S? S is the certain coordinate system. This is the S coordinate. And G is the shear modulus and thickness T. So if G and T are constant, and this will be simply QL twice A, and what is ds integration? Total length, right? Total length, I will say S0 and GT. Now here, what is a Q? Q is this shear flow, okay? So this is shear flow. So this is a stress and this is a rotations for the thin wall. Okay, that's the topic, a major two-point result we studied in thin wall chart. For the closed section, well, torsion of this open section is not so important, okay? You may neglect that. Torsion of the open section is not so important. Now, second part is what? Second part is the issues in beam, chapter 12. Issues in beam. What we covered in that section is that unsymmetric. Unsymmetric means, you know, the beam, a cross section may look like this, and so on. And so we can have I, YY, I, ZZ, and I, YZ. So using the Mohr circle, we can calculate I2 and I3 for principal moment of inertia. So that is the kind of issue in unsymmetric. And another point is that shear center. What is a shear center? For example, let's say we have an unsymmetric, like this beam. And we apply certain load. And what is the concept of a shear center? We didn't drive the complicated equations, okay? Which you don't have to. But the concept of the shear center is that we can apply a force here and there and any place. The shear flow will create it. Something like that, and always the maximum at the neutral axis. Shear stress is always a maximum at the neutral axis in case of a bending. Okay, that is an important point, right? So in final exam, I may ask where the maximum shear stress occur. You just say, you don't have to solve solve for a number. I want you to understand the general behavior and concept. So anyhow, what is a shear center? Shear center, for example, this triangle, shear center is located here. So if we apply the vertical force, and vertical force is passing through that shear center, it will not twist. If the shear force does not go through the shear center, then this beam will not only bend, but also twist. Okay, so this is on certain sections. When we apply the force, this structure will certainly a bend, right? But bend, depending on the where you apply, this not only bending but will twist. So shear center is defined as a point here. Then if I apply the force, same force, which pass through that shear center, then this one does not twist, only bending. Okay. Okay. That is the well, in advanced mechanics, we need to study more. But for you, this class, the definition of a shear center is that's all you need to understand. So issues in beam. So unsymmetric. Okay, unsymmetric. I just want to tell you this is unsymmetric, and bending. And bending, not only this bending, but it may have a this bending as well. So I apply here, so this one will bend like that. You follow me? So if this is a symmetry, if I apply force this way, it will like bend like that. If we apply here, it's just bending like that. But this is unsymmetric. One load may cause not only this bending, but also this bending, okay? And also shear center concept, it gives a twist. So remember there are three different twisting, curvature. One is this, and that, and this. So these are all curvatures. And for arbitrary cross sections, those three curvatures may occur at the same time. What is that? Curvature 1, curvature 2, and curvature 3. Okay, this angular rotation is also curvatures. So that is the kind of issues in beam, and we kind of understand. That kind of behavior may happen. But in simple beam, symmetric and simple beam, you should be able to get a beam theory is that EI V 1, 2, 3, 4 equal QX. Okay, so this one of course comes from the equilibrium. Here V and V plus dV, and then moment plus the moment, and moment, and there is a Q, okay, QX. So vertical equilibrium will give us dV dx equal minus Q, and moment equilibrium give us the moment dx equal minus V. So, and then another one is the moment equal what? EI curvature. Curvature is what? EI V double prime. That is the deflection. So we combine them all. We put these things into here, and so the final equations we will have is the EI with 1, 2, 3, 4 equal QX. That is the Gaboni equations, meaning that combining two equilibrium equations and one stiffness. So now when we solve this one, all kinds of a beam, like a clamped on the left and the free, and any beam problem, like you can solve by solving this fourth order differential equation. When you can easily integrate on both sides, right? So after integration, how many integration constant are you gonna have? 4, yes. 4, there will be a 4 integration constant, C1 and C2 and C3, and C4. How do we determine these four constants? Right, boundary conditions, always two boundary conditions at x equals 0, two boundary condition, another two boundary condition at x equals L. So boundary condition always either V, V prime, and EI double prime, and EI triple prime. So what is this? Deflection. What is the V prime? Angle. What is the EI double prime? Moment. What is the EI triple prime? Shear force. Yes. So you can either this clamped simply V equals 0 and V prime equals 0, right? So if you have this one, oh, there's a moment equals 0 and shear force equal some for P. So in this case, you can say minus EI triple prime equal P. So basically, this is the very powerful method to solve all kinds of deflections. Once you have all deflection, Vx, you can have a V prime as an angle, double prime as what? Moment distribution, and triple prime is the shear force distributions. Okay, so this is a very typical procedures to solve a beam problem for any external load or any boundary condition. One important point is that how you specify the Q. Okay, for example, let's say you have a very concentrated load. How are you gonna specify Q? That is the one important, could be important point. So we use the singularity function or whatever, but you don't need to cover that. Okay, but just conceptually understand. There's a QX. And QX can cover many different types of load, a parabolic and concentric load and moment and so on. But main point is that we have a fourth order differential equation which was derived from equilibrium and stiffness, this 3-1, and we need a two boundary condition for each side. So if we have a Q equal 0, I'm sure you can easily solve that for any boundary condition, right? And okay, so this is a simple beam theory, and this is the issues in beam. The reason I emphasize this simple beam theory is that those who took my class in the first semester already went through all this topic. But those who didn't take my class, you didn't study about this beam deflection, right? But don't worry, it's very straightforward this way, differential equations. I can, for just exercise, let's try to solve one simple problem, okay? For example, let's say we solve this one. Very typical, but let's say we apply the P here, and then we like to solve how much delta. There, not only delta, there will be, imagine this one is a deflect like that. So not only delta, but also we will have a theta, right? Now, this is very important. The load we apply is a force P. Force P, but look at this surface. It will deflect. It will deflect, but this one not only deflects, but it will rotate, right? Look at this angle, as it was a flat, and then when you apply, it will certainly deflect. If there's only deflect, this will like that. But there will be also rotations, right? So this one is a rotate. So there is a deflection, and this is the angle of rotations. So two deformation, a deflection and rotations. So let's try to drive these terms using differential equation. We can do it very quickly, but especially for those who don't have experience, you need to keep practicing, following my procedures. Okay, simply any beam theory, differential equations, EI, V1, 2, 3, 4 equal QX. And what is the QX here? From here to there, did we apply any force? No. So simply 0. And how about the boundary condition? Well, here is the deflection is 0 and angle is 0, right? Because this angle always remain a flat. So not only deflection, but also angle does not rotate. So V equals 0 and V prime equals 0. Now here, force P is a shear force. Shear force is a V triple prime, and minus this is a shear force, this is a P. Let me ask, why this is the shear force? We do know that this is a moment, right? Moment EI V double prime. This is a 0. But as I mentioned, we do have this relation, equilibrium, right? So if moment equal this one, we put it here, then EI, one more time, triple prime equal minus V. Okay? So this, a triple prime is the shear force. It comes from basically moment equilibrium. So this one, a shear force at every point, but especially that point, the shear force V is given, and this is the one. So moment equals 0. So this is the 1, 2, 3, 4 boundary conditions. Okay, that's all you need to have, and let's do integrate EI V 1, 2, 3 and constant, right? And EI 1, 2, one more integrations, right? We integrate one more time, and C1 x squared plus C2 x plus C3, right? Now integrate one more time, EI V and 6 C1 x3 plus C2 x squared and C3 x plus C4. How many constants do we have? 4. How many boundary conditions do we have? 4. Always differential equation is fourth order, and always a 2 boundary condition, totally 4. So which will determine all integration constants. Okay, so this is at x equals 0, and these are all at x equals L. So x equals 0, which means that, okay, using these two equations, because these two, x equals 0 means that 0, 0, C3 is what? 0, right? Now, deflection at x equals 0 means 0, 0, 0, and this one, this is what? Also 0. So C3 and C4, it's very easy, we got 0. Now, we have two more, which is C1 and C2. To calculate that one, we use this boundary condition. Let's say this 3 triple prime equal P, this is a C1. So this is what? Minus P. Okay, from this condition. And the second, the moment at x equal L means that we put the L, this is what? 0. So C1 equal minus P, C2 equal P and L, right? No? Yes, it's a plus, right? And C3 and C4 are all 0. Okay, that's all we need to have. And then let's put it back, Vx at the last, and then C1 is minus P6x3 plus 2C, what is the C2?
P.
Right, PL, so PLX square. So, okay, that's it. This is the AEA solutions. Okay, it's good that we have all deflection curve. Deflection curve. Ah, good to know. Oh, this is the third power of the polynomial. And also, this is the angle. Ah, this is the second power, and so on. Now, can we get a EI at the delta? What is the delta? Huh? How we get a delta? Delta is simply V at x equal L, right? Right? So L means that EI and L minus PL3 plus PL3. What is this? 3 EI PL3. Good to remember this equation. PL3 divided by 3 EI. Deflection, which means that deflection is proportional to P and inversely proportional to EI. But pay attention, a third power of L. So if you double the length, the deflection will increase by 8 times. And also, what is the theta? What is the theta? Theta is the V prime at x equal L, right? So, so here, a EI and C1, what is the C1? Minus P and L square, and plus C2 means PL and X and square. Okay, so this one, a what? EI PL square. This is a theta. Okay, please remember this equation. Theta PL square divided by 2 EI, delta PL3 divided by 3 EI. A little bit, we have to go through a little bit of steps, differential equation and boundary condition and so on. Okay. Last one I like to emphasize is the energy method. Well, there is a buckling one. Okay, I will go through a buckling. What is a buckling? When does it happen? It happens to any structures, especially when the structures under what? Tension or compression? Compressions. Structures become very unstable when subject to a compression. Very unstable. What it means unstable? Okay, here I mean there is a complicated equations, differential equation and so on, but we engineer need to understand the physical behavior. let's take a look at this paper. The behavior of this paper, behavior of wind turbine blade, behavior of all the airplane wing, same. Okay? So let's say this one, we apply, let's assume it has a little bit bend like that. And now I apply the tension. Do you see what's happening? These deflections is decreasing or increasing? Gradually decreasing, right? When this subject to tension is always a decrease, and then like that. So structures become straight and straight and straight, and finally it supports the load very effectively, right? But on the compression is the other story. I mean, reverse behavior. Compress, and deflection will increase, right? Increase. Once it increase, this here and there, this distance is increasing, right? So this force will cause more moment at that point. Why? The moment at that point is P times this distance, right? P times this distance. So moment at here is, as you can see here, it bend more and more, and finally it's very unstable, right? So that's why structure under compression is very unstable. Unstable means it doesn't want to stay as they are. It wants to change the configuration, different position. But tension always goes to one position, one configuration. No matter where it was, its tension is always goes straight, right? If you say starting from here, it always go there. It always go there. But the compression, even though it was a straight, okay, it was a straight, but like that. Why? Because that one is a very small, tiny, small deflection, and then it wants to give up. It cannot support, and then deform, and then once it deform, it just go away, diverge, like to stay away from the neutral positions. That's why when we explain the buckling, we often use this schematic diagram, which is the unstable or stable. See, unstable means that look at this ball and up on the hill and or stable. So this one, let's say structures under compression. So a little bit of a deviation means like that. So if these guys stay a little bit over that, it just go that way, right? It doesn't want to stay at the point. If you have a little bit of a deviations, and it goes like that. So what I mean by little bit of deviations is that any structures, any material have a small eccentricity or defect. So even though you apply the load, it becomes unstable. Whereas you have a structures, say you put it here. Put it here means that you have some deformation. But this tension will bring back straight, means that this goes back. If we have a small deformation, but tension bring this back to a straight. So here, always go back, stable, right? So structures under tension or compression is totally different behavior, okay? So this is leading to a buckling, and as I explained, this is a huge tower crane and a lot of load. So this kind of structure will subject, and these structures wants to support compressible load, but at a certain point it buckles. So it buckles. It happened much lower force than material failure. So very important. Well, there is a little bit of a differential equation which nobody likes, including myself. But one thing you need to pay attention is the EI 1, 2, 3, 4, and QX. That is the one we drive, right? But there is the additional term which is due to this compressive force. The compressive force times the vertical will give us, you see that V, and that is give us additional moment. So that is the additional term, and differential equation become more complicated. And to make a long story short, we have a P critical. This is the A beam under P and length and EI, and this critical load, higher always better, right? Higher means it does not buckle. So how to increase the buckling load? Well, it's always better to have a higher bending stiffness, and also L scale means shorter the better, right? Shorter, the less chance of buckling. Okay, so that's all I like to review. Now, the last one. Okay, I will try to finish ASAP so that you have a chance for your questions. Now, the last one is the energy method. Okay, energy method. Energy method. There are many different cases where you can use the energy method. For example, oh man. Well, my pen is out of battery. Energy method. We use the very simple equations such as this. Okay. See, we apply the force P here. Okay, this is the most critical part. We apply the force P here, and we obtain the strain energy. And energy is in terms of P, right? Now, when we derivative P, derivative this U with respect to P, what is this? This is the A, delta, where you apply the P. So delta is here, okay? This is a simple but very important point. In other words, say we apply the force here, how do we calculate deflection at that point? There will be some deflection. Am I right? This one, no deflection, but deflection will goes like that, and goes like that, right? So deflection at that point where you apply force P can be obtained like that. So remember this delta and P is the same location and same direction. That is the most important point student need to keep in mind. 무슨 말인지 알겠어요? 자, 이거 간단한 것 같아도 아주 그 중요한 포인트예요. 내가 스트레인 에너지를 다 외부의 force 함수로 구했어요. U is a function of external force. That's fine. Now, U derivative U with respect to P will give us the deflection at that point. 그러니까 내가 P로 미분하면은 그 P가 가해진 위치에서 P와 같은 방향의 변형을 구할 수 있는 거예요. 아셨죠? 아셨죠? 주의하세요. Same location and same direction. 뭐하고 P하고 델타는 same location and same direction. 그런데 what if we want to calculate the deflection at that point? 여기서 say 델타 1은 어떻게 구하면 될까? Where we didn't apply any force. 우리가 하중을 안 가는 데서 deflection을 구하려면 어떻게 하면 될까? These procedures cannot give us the deflection at that point. 방법이 없어요. 이 방법대로는. There is no way to just use that one. But we do make a little trick. Is that we 여기다가 we apply a certain force which we didn't apply real force, but we are applying certain force. It is called fictitious force, and then we express U function of F and P strain energy, and then we derivative F. Then this will give us delta 1, right? Because this delta 1 and this F is the same location and the same direction, right? So we got the result. And that is a function of F and P. But did we apply F? No. So at the end, we just apply F equals 0. Okay? That is a trick we have to follow. 지금 이해됐어요? Okay? So we have several cases that say we have a beam, we apply P, okay? Strain energy is simply a EI and moment square and dx, right? Moment x, well, you can have a P L minus x. Right? This one we have a P times L, there's a reaction force, and there is a P, and so certain position, you have a moment, and moment at X, this is the one. This is the moment you have to solve, you have to obtain for this. Now, the deflection at P, okay, at the P, what do you need to do? You derivative P, and this will be the a delta, okay? This is the delta. So this part can be spring or beam or any member. It's okay. As long as you got the strain energy for the extension, strain energy will be EA and P square dx. And for the torsion, this one is the GJ integration and torque T square and dx. And bending U equal EI and moment square and dx. So this is the one thing point you need to be careful. This is a concentrate load, P0 and T0 and M0. But this is a P is a function of X. Any P at X, okay? Any torque at X. And moment, any moment at function of X, which is different from this a load we applied at the end, right? So delta 0 at that point is the U by derivative P0 and theta 0 at that point angle is the T0 and U, and this is the well, this is any symbol is okay. Moment 0 is a U, right? But again, say you apply the M0 and then let's say, can we calculate how much it deflects, delta? We apply the M0 and can we calculate the delta? We apply the moment, then it will rotate, but there will be delta. How can we calculate that one? Well, theta 0 and moment 0 is relatively easy. And P and delta is relatively easy. But moment delta and P and theta, how do we do that? Do you understand my questions? So for that purpose, to calculate this delta, you need to apply a fictitious force P. We need to apply the fictitious P, and then moment is a function of what? And P and, I would say P0 and M0. And delta will be a strain energy with respect to P0, right? And then P0 should be what? 0. So I'll like to solve this problem right now with you, okay? I'm sorry we don't have a full note, but let's try to solve it, okay? So here we have a P, P0. And now how much delta and how much angle? Theta, okay? So first of all, this is a P0 reaction force. So moment will be a P and this is X and P0, and this is M reaction will be P0L. So P0L times X, right? So this is X, this is the moment at X. That's it. And strain energy will be 1/2 and EI and moment square dx. Now, delta, we derivative with respect to what? P0. So this one, we use the chain rule, simply EI moment, we derivative of moment, and then we derivative moment with respect of P0, right? This is a chain rule. And dx. What is this moment? Well, moment is here. So P L over X is EI. And moment, okay, moment derivative with respect to a P0. What is this? Simply L minus X. You see this, right? So dx. So here, P0 EI, and then we integrate. So this one will be L square. I mean this one. Okay, integrate. This is a L square minus 2LX plus X square. Integrate them, and 0 to L. So this first one will be L third, and this one will be L. What? Three, and this one 3L3, right? Okay, so this one disappear, and now what we have? So this is a delta. It's much more straightforward than solving. Where was it? Huh? Where was it? We remember. See this one, right? We went through all differential equation, we got deflections. And this one as the same as what? This one, right? Now, how do we calculate the theta under only P0? As I mentioned, we cannot solve it directly. We need to apply what? M0, as which is a fictitious moment. And so you got the moment X, and which is the a moment 0 plus P L minus X. That is the moment X. And put it here and do this. And now the theta will be what? A U derivative with respect to what? Huh? M0, right? So M0, which is moment EI, and M0, which next one will be 1 because M0 is this one, and dx. Okay, so we integrate them. What do we have? Okay, what do we have? Well, we have a EI and integrate them. PL square minus half. Well, P can be out. And this is L square. So this one is the PL square, right? So basically, we already consider M equal 0. So what is this? PL square divided by twice of EI, which is the same as what we obtained from differential equations. Right? Differential equations. I'm sorry, this one, right? Okay, so just one last comment is that one comment is that, what if we want to solve this kind of problem? Two different beam, and then apply the P. Well, how much we want to calculate the delta here? We apply force P here, but we want to calculate the delta here. How do we do that? We need to apply a certain fictitious force, right? So strain energies and F, and this will be the delta, and then at the last moment, F should be 0. That is the delta. Okay? Okay, that's all I like to review. And all this class, again, will be saved, a video, and then upload. Now, I'd like to hear from you about any questions on final exam.
지금 조식에서 U는 P까지의 전체 구간에서
Right. When you have this U, question is that, what is this U? U is the, as by definition, has to 0 to L and moment square dx. So from here to all, so cover everything. So for that purpose, this one, for example, L1, and this one is L2, then integration 0 to L1. This one, if you have a E1 and I1 and E2 and I2, and this one now is a constant, right? dx. And also L1 up to L, or L1 plus L2, and 2 E2, I2, and moment square and dx. So this one can be constant, this can be constant in this integration, right? So yes, this energy is the for whole structures.
이게 더 해야 되는 거 아니에요? 눈이 아니고.
Huh? Oh yeah, sorry. We have a summation. Okay, so this is a typical problem, or you can consider, what if we have this and that, and we apply the torque tip, right? How much it rotates. And okay, so yes.
저 문제에서 저 중앙 부분에서의 로테이션 값을 구하려고 하고 그럼
Right.
다른 m을 또 나.
Right. So his question is that, okay, this is a real torque we apply. And deformation wise, everywhere will have a rotate, 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 right? Everywhere is a rotate. Now, when we use this method, I would say T0, this is only rotation at that point, right? But what if we want to calculate the rotation at that point, or any point? For that purpose, what do you need to do? We need to apply another torque, say T1, okay? And then you express all this strain energy in terms of T0 and T1. How? Well, there is a reaction torque which will be T1 plus T0, right? So from here to there, all torque will be T1 plus T0, and here to there, the torque will be T0. So this is a total strain energy, and then we derivative of T1. This is the P1 at that point. And then final equation, we have to put T1 equals 0. Right?
저 위에 문제에서 그 P로 인해서 로테이션 세타를 구하는데 네, 중간 부분에서 할 때 그러면 없는 P도 놔주고 그리고 없는 M도 주잖아요.
Well, depends on the, if you want to calculate only delta, you need to only apply the force, right? If you want to apply, you want to calculate the rotations angle, you apply the moment. Okay? Just a moment. You don't have to apply two. 같이 갈 필요가 없지. 하나하나 따로따로 구하면 되니까. Well, there is a method called Castigliano theorem. Castigliano. This is the what I meant by energy method. But you don't need to worry much about this definition of Castigliano's theorem. And equation-wise, could be a little bit complicated, but that is the basically same as I explained. So if we want to look for this energy method in the through the internet, you say Castigliano's method. But all I explained is pretty much enough for you to understand for the energy method. I just want to emphasize one more time is that any strain energy method is one thing, right? Any deflections you want to calculate is the point where you apply the law. That just is the key point. Okay. Basically, why? Well, actually, this P and delta you multiply. What do you have? This is an external work. So if we put this a delta times a P minus strain energy, this is the called total potential energy, right? So this is the external work and this is the energy. I don't want to go too much detail about this energy method, but this is the physics in there. This P and delta has to be same location, has to be same direction, because this is the work and this is the energy stored in body. Okay? So that's the one thing I again emphasize. Keep that in mind, and you can apply to many complicated structures. Well, as you can see, we don't have not many slides, but that's the beauty of the energy method. We don't need any other theory. We just get a strain energy and derivative. We get all the deflections. Okay, any other questions?
문제 연습해볼 만한 기출 올려주시죠.
Well, okay, there will be no homework this week. Okay, there will be no homework, but I will happy to not assign, but share with you some sample problem. So it's up to you. You can try yourself. Okay. Any others? Last topic is the 3D beam. 3D beam, you should be able to answer to some questions regarding 3D beam, such as to solve this kind of problem. I'm going to explain, specify certain problem, and then a question can be, what kind of procedure you need to go through to solve this problem? Okay, so you just explain, specify, enter what, enter first, enter second, enter and third, enter, and so on. Okay, so as long as you understand how to run the program, there will be no problem. Is there anybody who doesn't know how to use a 3D beam? Well, if not, go ahead and practice, okay, yourself. And certain group, only one or two out of whole group members are running 3D beam. That is not good. All members in each group has to know how to run the 3D beam. So I promise there will be one question about the 3D beam. And I promise there are many questions about the energy method. Any questions, any suggestions? So half of the question will be like the questions you have to drive and get the solution. But the other half is like explain or answer. Explain the procedures and explain the concept and etc. Okay? And another important question will be, I will explain some real situation and you need to define the problem. And this is very important. You, all of you, are very used to the situation where all the problem is well defined. And you always start to solve. But you should be able to define the problems, meaning that, okay, there is a tree, and there is a lot of wind, and this tree is vibrate. What's the frequency? Now you should be able to define the problem. Simplification. Oh, the tree, I will model as a beam. And how big? Or a beam is like that. And how you model the wind. Okay, I'm going to use the distributed load. Uniform or some concentrated load with certain assumptions. And this is the very important skills you need to have. Okay, you as engineers and designers, and in industry, nobody gives you a mathematically defined the problems. You should you need to define the problem yourself or some condition and boundary condition. Then how to solve it? Well, once you formulate all the problem, then you can ask Google. You can ask another person to solve it. But the defining problem is the key part, actually. But so far, through high school and middle school, high school, or undergraduate school, you always given problems, statements, and then you solve. But in the real world, you should be able to define the problem mathematically. Okay? Okay, no more questions? So, I hate to say goodbye, but this is a time to close our whole semester. I hope you got you learned some from this class, and this is a pretty much new style of a class. And next year I will change more. Okay. Oh, you allowed to ask me any question through KakaoTalk. Okay, until this week, but only through group talk. 90 students, only group talk. Don't ask me personal questions. The reason is that I like to share the question all together. So you can listen to others' questions, or you understand the way I explain to others. Okay, it's important to share your video. So feel free, but don't ask too much. Okay, sometimes too many. But I'm happy to answer any questions until by this weekend. Okay, any others? Okay, so thank you so much, and hope to continue to see you. Thank you. Bye.
죄송해요.